So let me take a minute to share with you some personal experience of mine using an extrapolated prediction um, with a line of regression that I did in my term uh, working in material science and engineering. So what I've got here is the title to a paper that I collaborated on with another researcher. So this researcher, uh, Le Wang, was a graduate student in the chemistry department. This was his project that he was working on. Um, and what he was doing was he was working on these geometric organic frameworks. Now, these geometric organic frameworks also had manganese atoms in them. And these manganese atoms were magnetic. The manganese atoms were located at the corner and at the center of each of these tetrahedral organic structures. So tetrahedrons are four-sided geometric figures that kind of look like pyramids, but pyramids have five sides. A tetrahedron has four. And so you maybe can see these little orange um, little balls here on the corners, and there's one you can barely see here in the center of the tetrahedron. Those were the manganese atoms. And then you had, oxygen and carbon uh, atoms kind of connecting them and making this tetrahedral structure. Okay. Now, Le had approached me because he wanted to know if the manganese atoms were magnetically interacting within the tetrahedral structure. They were not expected to be interacting. Typically, two atoms will magnetically interact if they're side by side to each other, meaning if they have like a bond next to each other. But as you can see here, whenever you've got, kind of like a series of bonds, in between two magnetic atoms, you wouldn't expect any kind of magnetic interaction. They're just not close enough for that. So Dr. Morales, me, was asked to lend my magnetic characterization expertise to collaborate in this project. So I was making magnetic ceramic materials. And so when I was making magnetic ceramic materials, I used a device called a squid magnetometer, which stands for a superconducting quantum interference device. And because my specialty was in magnetically characterizing materials, this other graduate student kind of enlisted my help, asked me for my help to kind of lend my magnetic characterization uh, expertise to his project. So I measured the magnetic properties of Le's metal organic framework material from 300 degrees Kelvin, okay, which is about room temperature, down to 2 degrees Kelvin, which is just above absolute zero. And so below is the graph of the magnetic data that I measured. So I believe this is magnetic susceptibility, the inverse of magnetic susceptibility versus temperature. Yeah, inverse molar susceptibility versus temperature. And so as you can see in the data, there is a temperature range from about 20 degrees Kelvin, 20 degrees Kelvin, which is right about here, maybe right about here, up to 300 degrees Kelvin, where the relationship between temperature versus inverse susceptibility is linear. So you can see all these data points. The relationship between temperature and inverse susceptibility is linear. It becomes nonlinear at lower temperatures, meaning it's no longer a straight line. It kind of dips down towards absolute zero. Now, I had measured, data down to 2 degrees Kelvin, okay, which is almost absolute zero. And so because of that, I kind of learned that that the inverse susceptibility uh, kind of veers down and away from this line of regression, which is the relationship between temperature and inverse susceptibility. So had I not measured that, I could have maybe assumed that it continued to be linear all the way down here, okay, when in fact it's not. But remember I told you that extrapolating from a line of regression is risky. So you have to know what you're doing. But so this was an example where the linear portion could be extrapolated to intersect with the y-axis. So if you have an inverse susceptibility of 0, where does this line of regression intersect this temperature axis? And so it intersects the x-axis at negative 23.7 degrees Kelvin. So right here at negative 23.7. And with this kind of magnetic analysis, if the x-intercept is negative, okay, like it is, the x-intercept is negative, that means that pairs of manganese atoms are interacting very magnetically. So what that means is each atom has, I guess, to maybe simply say it, has like a little compass needle, has what they call a magnetic moment, which is a magnetic direction that you could think of as kind of like an upward arrow. And this would be like a north and a south, like you would see on a magnet. And if all of the atoms were arranged in the exact same direction like this, that means that they are magnetically coupled to each other. And this would be an example of ferromagnetism. But ferrimagnetism is, again, they're coupled to each other, but you have a few of them that not only are pointed downwards, maybe in the opposite direction, but maybe they're not as strong. Okay, so here's the north and here's the south. Here's the north and here's the south. So this, where you've got magnetic moments that are pointing like in an up direction and some are pointing down, but they're not as strong, that's an example of ferrimagnetism. And ferrimagnetic materials, aren't as strong magnetically because they're kind of working against each other. Okay. So from the slope of the line of regression, which is the linear portion of the graph, I was able to use that. I was able to use that to calculate the effective magnetic moment to be 5.4 Bohr magneton. Now, an effective magnetic moment is you've got these manganese atoms in a tetrahedral geometry. And if you were to add up the magnetic moments of all 5 of these atoms, they would add up to 5.4. That's what it means to be the effective magnetic moment. So we know that we've got manganese in these 5 locations, but manganese comes in several electrical valences. They come in manganese 2 plus, manganese 3 plus, and manganese 4 plus. So each with different magnetic moments. 5.9 Bohr magneton, 4.9 Bohr magneton, and 4.0 Bohr magneton for each of these different valences. So it turns out that if you were to create a tetrahedral structure with manganese atoms, so where you've got one manganese 3 on a corner and a manganese 3 on the inside, and you had manganese 2 valences around the other three locations, or you flipped it where these were manganese 2 and these ones on the corners were manganese 3, then you would end up with an effective magnetic moment here of 5.5 and effective magnetic moment of 5.3. So it's possible that because I had measured an effective magnetic moment of 5.4, that in Luo's material, half of them were in the first configuration and half were in the second configuration. And if you take 5.5 and 5.3 and you add them and divide by 2, they average out to an effective magnetic moment of 5.4. So what I was able to do was I was able to come back, to Lo and tell him that the manganese atoms are interacting. They are magnetically coupling. They're coupling in a ferrimagnetic manner. And I could tell him that he could have a combination of manganese 2 and manganese 3 valences, either in this configuration or in this configuration in equal amounts to give an effective magnetic moment equal to that which I measured and calculated. And all of this from finding a linear portion of the graph that I could do a line of regression fit to, and then extrapolate where that would cross the x-axis. And in this case, you have to be careful when you extrapolate in what you do an extrapolated prediction, but I had very sound physics models and reasons to do what I did. Okay. So you just have to be careful about when you do that. So I just wanted to, share with you, kind of at a high level, how something that you're learning, even in an intro stats class, is used in professional scientific research. So this is when I was, in graduate school getting my PhD. And this was a paper that we published together and is now a part of the scientific literature that anyone in the world can read and learn from. And I get notices from time to time telling me that people are still reading this paper and learning something from it. So this was my little contribution to this paper. It was, had a lot more to it than that, but a section of it was about the magnetic properties of this material that Lou had made. So I was very pleased that I was able to offer, some help, in this regard to help kind of round out this paper. All right. Well, this is, part of what a materials scientist does. So let me know if you have any questions.